When autotune was invented, music changed forever. And at the heart of autotune is the pitch shifter. From pop music to
TikTok filters
to Nightcore and Alvin and the Chipmunks, pitch shifting algorithms have remained one of the most basic fundamental features in any audio editing software. But most of the resources about it are academic papers and articles with a lot of words. I don't like reading words, so I want to build up to one of the most prominent algorithms, the phase vocoder, from scratch with pretty animations instead of words. The first clue for how to make a pitch shifter is in the playback rate. This audio was meant to be played at 44,100 samples per second. But when I double the playback rate, the pitch increases by 1 octave. But the tempo also doubles. The duration is halved. We don't want that. This does tell us, though, that a pitch shifter and a time stretcher are one and the same. If we can somehow halve the tempo, but leave the pitch unchanged, that is, double the duration but retain the frequencies, then just playing back this time-stretched audio at double the playback rate will compress the duration back to the original, but double those unchanged frequencies. It turns out that stretching the time first, then doubling the playback rate will lose less information than directly scaling the frequencies. I'll explain that when I get to the Fourier transform. So, the challenge is to stretch out all the global relationships, but keep the local ones the same, since those determine the frequencies. A simple way to do this is to divide the input signal, or analysis signal, into little windows and move these windows apart in the output signal, or a synthesis signal. These windows should be big enough to capture and retain an adequate amount of frequency information, but small enough to represent only essentially an instantaneous moment in time. This clearly leaves audible gaps in between windows though, so instead we need to start out with overlapping windows. The distance between the start of one window and the start of the next window is called the hop length, or hop size. Now, this time stretching will change the global relationships and conserve local frequencies, but now there are audible discontinuities between each window, where the signal suddenly jumps. We need some way to blend between the windows. The trick is to increase the overlap and end up with overlapping windows. Then, the windows can cross-fade between each other during the overlap. This is where the window function comes in. The idea is to crossfade between windows, so each window fades in and out according to this window function. The window function can be anything, as long as it tapers out at the ends, but one of the most common window functions in audio signal processing is the Han window. It's sometimes called the Hanning window, but the guy's name was just Han? Anyway, after overlapping and adding, we have to normalize the synthesized signal, since there's no guarantee that the window functions sum to 1. Here's my implementation of this. I just used trial and error to find good window and hop lengths. This is how you calculate the scaling factor based on the number of semitones you want to shift the pitch by. Doubling the frequency raises the pitch by 1 octave, so multiplying by 2 to the power of n will raise it n octaves. There are 12 semitones in an octave, so this will raise the pitch by 5 semitones. The scaling factor is what I multiply the hop length by to stretch time, and later it's what I multiply the playback rate and, by extension, the frequencies by. First, here's the original audio. And here's the pitch-shifted version. So it did sound like a pitch-shifted version of the audio, but there was a ton of fluttering. Interestingly, it doesn't seem like this fluttering is apparent when shifting down. Anyway, to see what causes the fluttering more clearly, let's look at what happens when we time stretch a pure sine wave. When you overlap and add the next window, the troughs of one window's signal cancel out the crests of the other, and you get a mess instead of another pure frequency. The problem is that moving the windows disrupts the phase relationships between them. This can be mitigated by allowing a little leeway in the window placement and choosing a position that maximizes the waveform similarity, like the minimum of the absolute difference. However, there is no guarantee that there even is any good window placement, and you're often left having to just choose the least bad option. In practice, the waveform similarity is actually given by autocorrelation, which takes in a time lag and outputs the inner product between the signal and the lagged version of itself. The time lag with the highest correlation represents the optimal window placement. Unlike absolute difference, correlation takes into account signs. That is, the product of points with different signs will always be negative. This algorithm is called synchronous overlap add, or SOLA. There's a similar algorithm called waveform similarity overlap add. That one just adjusts the analysis windows instead of the synthesis windows. They produce similar results. Here's the code for SOLA. The only addition is this search for a good window placement. That removed some of the fluttering, but you can still hear a lot of it, especially in the violins. Audio processing in only the time domain just isn't powerful enough. But before I move on to the frequency domain, I want to mention that there are some more sophisticated time domain algorithms that take into account pitch estimation, for example. But my audio has multiple simultaneous pitches, so that's not too helpful. From here on, I'll assume you have a basic understanding of the discrete Fourier transform, or DFT. If so, you might have thought, why not just take the DFT of the audio and scale all the frequencies? Well, this would just do the same thing as changing the playback speed, except it would repeat the audio at the end, because it treats it as a periodic signal. The problem is that the Fourier transform is a global operation, and it's unclear what information each frequency really represents. But we can use the same method as before and divide our signal into overlapping windows. Taking the DFT of each window will give us the spectrum of the window, a set of phasors or phase vectors, complex numbers with both a magnitude and a phase, but often for convenient visualization, we just display the magnitude as a pixel brightness. After sweeping across our signal by the hop length and repeating, what we get is the short-time Fourier transform, often visualized as a log-scale spectrogram. Remember, each window represents an essentially instantaneous moment in time, so the STFT gives us complete control over the moment-by-moment breakdown of the phases and energies in each frequency bin over time. To time stretch the audio, we generate the spectra for new STFT windows by interpolating between the original spectra. Say, for example, the original STFT has 10 windows and the time-stretched STFT has 15. The sixth window of the new STFT starts 5/15, or 1/3, of the way across from the start, so it should have the same frequency magnitudes as the window 1/3 across from the original STFT. The problem is that 1/3 of 10 is between the third and fourth original windows, so you need to linearly interpolate between their magnitudes. This is different from before when we were keeping the number of windows constant but changing the hop length. The computation for the STFT is just a little easier when we keep the hop length constant and change the number of windows instead. After this, we simply perform the inverse DFT on each new window and add it to the synthesized signal. You might be wondering why we're time stretching again instead of just directly scaling the frequencies. You could scale the frequencies, but it's just a bit more complicated. Also, if you scale across frequency, you might bring some frequencies above the Nyquist frequency. You see, if a frequency gets too high, the samples will look identical to those of a sine wave at half the frequency. You'll lose the high frequency and instead get an incorrect lower one. This distortion is called aliasing, and it means that the discrete Fourier transform can only reliably calculate half as many frequencies as there are samples, plus 1 for the Zerwith frequency. This is called the Nyquist-Shannon sampling theorem. You have to either throw away the higher frequencies or resample the waveform, and that would just be a time stretcher. So we're gonna make a time stretcher by interpolating the magnitudes to fit a different number of windows, but watch out. Just like before, we have to figure out how to fix the phase relationships over time. To understand how the phases align across time, you'll have to know that the discrete Fourier transform is lying to you. Or at least, it's not telling the whole truth. I mean, of course there aren't only integer multiple frequencies in the signal. But somehow, the magnitudes and phases of fractional frequencies are encoded in nearby discrete frequency bins. We need to figure out how to extract the true frequencies from the discrete frequencies, since it's really the phases of these true frequencies that we're trying to align across time. Typically, to approximate the true frequencies from one DFT, you might use something like spectral peak interpolation. But there's a special quality of the SDFT that gives a much easier and better solution. Let's break it down again. Here is a signal, decomposed into its frequencies, traveling through multiple SDFT windows. There are many different frequency bins for each time frame, but let's just focus on one frequency bin, and let's make it clearer where the windows are. Theoretically, this blue wave is some true frequency that is close enough to the discrete frequency to activate the bin. When the true wavelength happens to exactly equal the hop length, notice how the true phases of all the windows are the same. Each window signal looks identical. This suggests that there's some pattern relating the phases of successive windows and the frequency of the signal. So let's see what happens when we run a pure sine wave through the STFT. For now, we'll ignore the discreteness of the DFT, so the formula for the cosine wave in this window is the true frequency times time plus phase. When we move the window, we essentially shift the time over by the hop length, or n times the hop length, where n increments by 1 each window. But this multiplies out into frequency times hop length, which is a constant term with respect to time. So it manifests as a linear offset to the phase. Do note though that the phases will be wrapped around 2 pi. You can think about it like this. The phase of the nth window should equal the phase of the previous window, plus the true frequency times the hop length. But the hop length is constant, so the true frequency directly correlates with the phase difference. So when we increase the frequency, the phases should follow an increasing linear pattern. That is, the difference between the phase of the current window and the phase of the previous window is the same. The keen among you may have noticed that these differences are not in fact the same. What happened? This is where spectral leakage comes in. The discrete Fourier transform treats the samples as part of a periodic signal, so if the window doesn't catch an integer number of cycles, it spends a lot of frequency information trying to reconstruct these unnecessary discontinuous jumps. So the window function helps to both blend between windows and make sure the signal starts and ends at the same value. Any window function you apply will produce some spectral leakage because it will change the signal. Different window functions will do different things to the frequencies, but in general, the Hahn window works well for most cases. Now, after applying the window function, the phase differences are the same. Well, this one's different, but it's really close. I think that's just a numerical error. Anyway, this is the key insight that solves everything. You don't even need to calculate the true frequency. It doesn't matter. The only thing that defines the true frequency is the differences between the phases between each window. So, like with the magnitudes, we simply interpolate the phase differences, or the phase derivatives with respect to time, if you want to think about it like that, across the final number of windows, then do a cumulative sum of these new phase differences across time to get the new phases. Here's my implementation of this. You can see I really took advantage of vectorized operations to speed this up. Also, after calculating the phase derivatives, I had to wrap them around 2 pi so they wouldn't interpolate across multiple wavelengths. Here's how it sounds. Okay, so the fluttering is pretty much gone, but what happened to the marimbas? They started out alright, but a second in they got all smeared. The problem is phase drift. Before, when we were moving entire chunks of audio, we weren't disrupting the phase relationships between the frequency bins in a single time frame. The overall shape of each window was preserved. But now, because we're shifting the phases of each frequency bin based on temporal relationships instead of interfrequency relationships, the shape of the waveform gets all messed up, and the transients, or sudden abrupt events in the signal, like percussive marimbas, are lost. So there are two conflicting phase relationships. The temporal relationships we just calculated assume a steady frequency across time, so they're better for sustained notes, like violins, where each frequency is constantly audible and there's no hard or sudden beat. The shape of the waveform doesn't really matter because nothing interesting is happening in the window. But when there's a transient, the shape of the waveform is what makes the impact. We can calculate a crude approximation for when a transient has come by just seeing if the energy of the frequency bin increases by a big amount proportional to the previous energy. If so, we simply reset the phase of the synthesized STFT to equal the phase in the corresponding original time frame of the analysis STFT, which will exactly reproduce the original waveform shape. Finally, this is the ultimate product, a phase vocoder that time stretches audio and resets the phases at transients. Just for comparison, here is the pitch shifting built into the Librosa Python module, which is what I've been using to calculate the STFT. This, of course, is not the whole story. There are so many papers out there, and AI phase reconstruction looks promising. But I think I've had enough of phases for today.